going to relate is an experience that we have done with high school students, senior high school students in Uruguay, to arrive to the concept of integrating. The students already know how to find the derivatives of functions, but we need to go to the next step. Integration have several applications, but one of the first ones we can think of is to find the area under a curve. Here it was given to students, or the students were asked to build this graph, and the goal was to calculate the area between this quadratic function and in an interval 1, 3, sorry, this piece that is painted over here. They were asked the students to estimate. They didn't have more tools than that. So if we can count here, we have one unit of area, 2, 3, 4, 5, 6, 7, 8, 9, 10, and maybe 11 with this 2 and something. A little bit more than 11. That would be the area of this, estimating the area of the painted part. Area estimated, let's say 11.2 unit squares. That is 1 unit. That's what maybe many students have estimated. Some more than that, some less than that. And well, that was the starting point, the experimentation. And once they have done the experimentation and they have given several different results, but they were all similar, we went through to introduce the concept of integration to find this area in an exact way and fundamentating the theorem that underpins that calculation. To differentiate and to integrate are inverse process. Now, let's say that we have the function f of x equal x squared. Integration and to differentiate and to integrate are inverse process. If we have fx x squared, we find the derivative, which is 2x. If we integrate and we find the indefinite integral of 2x dx, that will be exactly x squared. It's the same thing as when you square a number and then you make the square root. You arrive to the same place. Let's put another example. Let's say we have g of x equal logarithm of x. The derivative of logarithm of x is 1x. And then the indefinite integral of 1 divided by x dx, we arrive to the initial function that are logarithm of x. Even though to differentiate and to integrate are inverse processes, that doesn't mean that they are equal, easily to solve, or they have the same difficulty. To find derivatives, maybe with a table of 30 or 40 or 50 functions, that's enough to find the derivative of many functions. But to integrate, you need a table with more than 20 cases, because the integral it's more complicated and it changes very much depending on which function you want to integrate. Let's explain a little bit more about these symbols here. What do they mean? This symbol reminds an S, a stretch S, because it represents a sum of something, a summation of something. And dx is called differential x, and it's a delta x, an interval on x that is infinitesimal. That is, that's as small or as little as we wish. And that's the symbol that it appeared over here. We are going to find out how that comes in the process, how that comes. Well, let's find some formula that we're going to use to integrate. We know that to find the derivative of x to the n, that is n x to the n minus 1, raised to the n minus 1. So, to find the derivative, we put the n multiplication in the beginning as a product, and then we have to subtract 1 from the exponent. The integration of x to the n dx x is equal to x raised to n plus 1 divided by n minus 1. So here we increase and we divide. Here we put the same and we subtract 1. Let's apply this to some function and let's see if this works. Let's say we want to find the derivative of x cubed. That will be 3x squared. Let's use this formula to integrate 3x squared dx. This 3 stays in front, and then we have to put x cubed divided by 3. 3 cancels with 3, and so the result is x cubed, which is exactly the same function we started with. When we integrate, when we find an indefinite integral, there might be a constant over there, but we are going to talk later on about the constant. It doesn't affect to our reasoning. So we see how these are inverse process. We find the derivative and then we integrate and we arrive to the same thing. Wow. Let's go now to find the formula which will allow us to calculate exactly the area under this curve. And we are not just to plug in the formula. We are going to arrive to the formula, to reason from what we already know to reach the formula which will allow us to find exactly the area of the painted zone. Let's write some notation, and then we're going to use the mean value theorem. If we have an f of x, a function, and we find the derivative, we write this f prime of x. And if we find the integral function, we will write this with f, capital F. So that's the sense to find the derivatives. And in the opposite way, that would be integrating. We integrate this, we find this. We integrate this, we find this. Let's put the mean value. This states that hypothesis that if f of x is continuous in a closed interval AB and has derivative in the open interval AB, therefore the thesis says that it exists a C that belongs to the open interval AB, so that the derivative in C is equal to FB minus FE divided by B minus I. Okay, well, we are going to adapt this theorem, but instead of applying to fx, we are going to apply it to this function. And we are going to rewrite it. The mean, let's do a change of notation for the mean value theorem. And instead of applying to an f of x, we are going to apply it to a capital F of x. So the mean value theorem would be, let's underline it with red, it will be hypothesis. We have a f of x continuous in AB and with derivative in AB. So the thesis is that we can find a C that belongs to the open interval AB in order that the f prime is the derivative. In this case would be the derivative of fx, which is fx we have written already. fc equal fb minus fa divided by b minus a. You remember that we said that the derivative of this function was fx and the derivative of this function was f prime. And so that thesis we can write it otherwise. That is, we can multiply this b minus a by here. So we could write this fc times b minus a equal fb minus fa. That will be the thesis for our mean value theorem applying to capital F. Okay? Well, now we are going to see how this theorem works to find our formula to find the area, the exact area that we wanted to find. Let's leave this thesis here in order that we can erase the rest of the theorem. Let's draw a random function which we want to calculate its area. And we have here A and here B. Our goal would be to calculate the area between a graph A and B. Put it on green slightly. That's our goal. So we can divide the interval IB into equals sub-intervals of the same size. And so we can put here x1, x2, x3, and then here we are going to arrive to x minus 2, x minus n minus 1, and there we have b. And so the size of each interval it's the same. So we would say that x sub 1 minus a is equal, the size of this is equal to x2 minus x1 is equal to x3 minus x2, and similarly x n 9 minus 1 minus x n minus 2 equal to be x n minus 1. And this length we are calling to call delta x. Well, since we are supposing that this fx is continuous and has derivative, so we can apply the theorem, the mean value theorem, to write that there is a c in each subinterval in terms that f of c1 times delta x, that will be delta x, is equal to f x1 minus f x2. Similar in f2, f of c2, here is going to be a c2 times delta x is f x2 minus f x1, and f c3 delta x is f x3 minus f x2, and we can continue that f of c n minus 1 delta x is equal to f of x n minus 2 minus f n minus 1, sorry, f of x n minus 2. And the last one will be that f of cn times delta x is going to be fb b minus f x. If we add all this, we make a summation of all this. I'm going to write it here on my right. But it's something very interesting. That this one cancels with this one. So here is a. Because x1 minus a. Well, if we add all this, we can easily see that there are many things that cancel each other. For instance, this is f x1, this is minus, this is plus, and use another color, and cancels with this one, and so on. This one will cancel with the following of this, and this one will cancel with a positive. This one cancels with this. This one will cancel with the forward. So the only ones that are left are f of b minus f of a. And here we have a summation of, we have a summation on the right of f of s y is going to be delta x, all these summations, and y is variation between 1 and n, y and n, and those are delta x. This is equally simply to f b minus fa. And now we have to pass to the limit. That is, to make those delta x as small, as little as we want, infinitesimals. And so we are going to write the limit when delta x tends to 0 of the summation of e1 to n of x epsilon 1 delta x. And the limit of this, there's no variable here, so that will stay the same thing. Let's write it for the sake of notation. This is the area of one rectangle, and the summation of all the rectangles is the area that is painted, that we wanted to find. And so, to find exactly the area, we have to put the limit when delta x tends to 0. So we write limit of the summation from e equal 1 to n of f c1 delta x, sorry, here it was cy, equal fb minus fa when delta x tends to 0. This infinite summation, we said that it turns out to be the integration. This sum is an infinite sum from a to b. Fc, since c is going to be infinite values, is f of x. And delta x, when it tends to 0, turns out to be the differential x. And that's fb minus fa, which is the fundamental theorem of calculus. Let's now calculate that area in exact form. Following the fundamental theorem of calculus, the area between 1 and 3 of minus x squared plus 3x plus 4 dx is going to be f3 minus f1, which f is the indefinite integral of this function. So the indefinite integral of this function is going to be, following the rule we said, it's minus x cubed divided by 3 plus 3x squared divided by 2 plus 4x. When we find the derivative of this, you get this easily. The 2 cancels out, and here 4x. Sorry, if you divide by the derivative, is this. To verify. And so that value we have to evaluate it in between 3 and 1. That is f of 3 is, we plug here the 3 is minus 3 cubed divided by 3 plus 3 squared divided by 2 plus 4 times 3. And that will give you, all this operation will give you 33 halves. And f of 1 is going to be minus 1 cubed divided by 3 plus 3 1 squared divided by 2 plus 4 times 1. And that is going to be minus 31, 6. we have to subtract those two numbers. Is 33 halves minus 31/6. And that's going to give us 34 thirds, which is approximately 11.3 period, infinite, which was close to the value we first estimated the students at the beginning of the lesson. But this is the exact value of the area. So we are going to calculate this area, which we estimated that was between 15 and 16, or between 15 and 17. And we have to follow in the fundamental theorem of calculus is the integral between 1 and 6 of 9 divided by x differential x. We could write this like 9 times 1 divided by x. The constant doesn't affect, but the indefinite integral of 1 divided by x, we found earlier that it was logarithm of x. So that would be 9 natural logarithm of x between 6 and 1. And to write this, we usually use this notation: 6 and 1. That means we have to calculate this on 6 minus this on 1. That will make 9 logarithm of 6 minus 9 logarithm of 1. We know that logarithm of 1 is 0. So the answer for that area is an irrational number, which is 9 logarithm of 6. In the other case, it was a rational number. Now it's an irrational number. And so we calculate that value. 9 times logarithm of 6. And that gives us approximately 16, which said before, 0.13, or 126, which is a value that is similar to what we estimated, which gives us an indication that it's very probably is correct. And so this is the first application of integration, which had plenty of applications, but we see how it works, and we also found where this formula comes from. And so it's a good start for beginning to learn about integrals, with 2 examples and with the formula that we found step-by-step reasoning where does it come from. Well, I hope this helped to progress in the learning of integrals. Thank you.